Good Tuesday morning. We're back. Today's lesson a little bit longer. It's going to take us a little bit of time to get through this one. This is sort of the foundations of the next couple days, and I mentioned last class that we were going to be using ice tables and equilibrium constants. So here's where we tie chapter 15 skills into chapter 16 acid-base equilibrium. And so it all comes together today. By the way, I decided to wear a hat today, so I don't know, the lighting's not great. There we go, that's a little better. This is Alterra. My youngest daughter, worked for them last summer, so she got a couple of free hats. They're an engineering company in Red Deer and Edmonton. So, okay, here we go. Acid-base strength and the equilibrium law. You'll need your data book beside you for this one. We're going to be using that table of relative strengths and those equilibrium constants from the table for our Ka values. First of all, a little review of strong and weak acids and bases. So as it says here, you can now predict the approximate equilibrium position of any acid-base reaction, greater than 99, greater than 50, less than 50. And we can use the equilibrium law to better predict equilibrium positions for acidic and basic solutions. So that's what we're going to be doing today. But first, I want to do a little review. So we're going to use the vocabulary strong acid, weak acid, strong base, weak base, and the idea of concentrated versus dilute. So this is a little bit of a review from Chem 20, a little bit. So if we have a hydrochloric acid and it's 2 moles per liter, how would you describe the strength? Is that strong or weak? Hopefully you remember that hydrochloric acid is one of the big 6 strong acids. 2 mole per liter, we would use that relative term and say that that is a concentrated solution. It's kind of comparative. So if we're going to compare it to hydrochloric acid that is 1.6 times 10 to the minus 4, we would say that solution is dilute compared to this one. So it's the same acid. They're both strong. One is concentrated and the other is dilute. Okay, NaOH, what do you know about sodium hydroxide? Is it an acid or a base? Is it strong or weak? So hopefully you recognize that is a strong base. All ionic hydroxides that have high solubility, in other words, they dissociate 100% to give us those hydroxide ions, are strong bases. And the top one is concentrated, 3 mole per liter. And then this one, 0.00001 mole per liter is dilute. Okay, and the best for last, HF, acid or base, strong or weak. Hopefully you recognize it as an acid. You could look it up on your table and discover it's a weak acid. It's weak, but it is concentrated, and that's unusual to put those two words together. Students confuse them, and they think if you're strong, you must be concentrated, and if you're weak, you must be dilute. Not at all. They are two very different properties with different terms to describe them. NH3 looks like an acid, but hopefully you remember ammonia is a base, and it is a weak base. And this one is dilute. So we've seen weak and concentrated, weak and dilute, acids and bases, strong, weak, concentrated, dilute. Okay, so that's a little bit of a review, some vocabulary for you. By the way, if you were calculating a pH, POH, you can only do it easily for the strong ones because it's 100%. For these weak ones, we're going to have to use equilibrium. So that's where we're headed today. Okay, so I'll already mentioned this. Strong acids react quantitatively with water. So if we had 2 mole per liter of nitric acid, we would get 2 mole per liter of hydronium. And if I wanted to calculate the pH, I would just go negative log of 2. That would give me a very low pH. Weak acids undergo partial ionization in water. How far the reaction moves forward is determined using its equilibrium constant. And for acids, that's called its Ka, or acid ionization constant. So Ka will be new for you. However, the way you set up Ka is just like you would set up any other equilibrium reaction. It is products over reactants. And these acid-base questions are always 1 to 1 to 1 to 1 ratio. So they're kind of easy. Okay, they all follow the same pattern. 1, 1, 1, 1. Now I want you to look very carefully at this equilibrium expression, and I'm curious if you've caught the one unusual thing in it. So look at our reaction, HF, H2O, H3O plus, and F minus, and then look at the equilibrium expression for that reaction. And what do you notice? Correct, it's missing water. Why do we not have water on the reactant portion? Correct, because it's a liquid, and we don't include liquids because liquids don't have a concentration. Concentration only happens when you have moles in liters, aqueous solution. So solutions have a concentration, and gases, dissolved in gases, have concentration. Liquids do not. So water is out. So that's your basic pattern for a weak acids equilibrium expression. Okay, moving on. First type of problem. Calculate Ka, or the acid ionization constant, if you're given amount concentrations for a weak acid. So here we have a 1 mole per liter solution of acetic acid. That is a weak acid. And we know its pH. What is the Ka value? Okay, so let's use a Bronsted-Lowry reaction to figure out what's going on here. Acetic acid is CH3COOH, and all it is acetic acid in water. So there's your weak acid and your weak base. Bronsted-Lowry will transfer that proton from the acid to the base. There's where our hydronium comes from. Okay, now because this one is in equilibrium and it is less than 50%, we need an ice table. So this is the new part. Okay, what do we know from our ice table? We know we had an initial 1.00. We get to ignore water because it's a liquid. It has no concentrations, so it's not part of our ice table. And we know that initially there was no product, but as soon as this thing starts to react with water and donate its protons, its concentration changes. It starts to lose X amount. There is 1 mole per, or not one, a ratio of 1 to 1. So that means we will gain 1 amount, and lose 1 amount. Coming back to you, these ice tables, hopefully. It's starting to look familiar. Okay, lose 1 amount. All right, so to figure out our equilibrium concentrations, we add the top 2 rows. 1 minus 1x, 0 plus 1x is just 1x, and 1x. Okay, so we have our ice table, and we have a way of figuring out this guy, and we have it from this right here. If we know that the pH is 2.38, we can figure out the concentration of hydronium. If pH equals 2.38, concentration of hydronium is 10 to the negative pH. 10 to the negative 2.38. And 10 to the negative 2.38 is 0.004168. Or 4.168 times 10 to the minus 3. So that is our value of X. Okay, well that's good. So now we have all 3 of our equilibrium concentrations. And 1 minus, which is 0.9958. Okay, if we have all of our equilibrium concentrations, we can now solve for our Ka value. We need the equilibrium expression. Ka is products over reactants. So concentration of CH3COO minus, equilibrium concentration of the acetate ion, and equilibrium concentration of hydronium over, so that's products over reactants. And again, we are ignoring water. So all we have on the bottom is the equilibrium concentration of acetic acid. And we have all three of those values. So my calculator, this is already, I would store this in X. And then I would just be putting into my calculator X squared over 1 minus X. But for here, I'll write it all out. 0.004168 squared over 0.9958. And drum roll, please. We get a Ka value. Why did I not calculate this one? I didn't put it in, but it's right there. 1.7 times 10 to the minus 5. 2 sig digs because of the 2 decimal places in that pH. This one has 3, this one has 2. So that is how you use an ice table for a weak acid in water to figure out the concentration of hydronium ions, which is X, and then the equilibrium constant or acid ionization constant. We use the equilibrium law expression, substitute in, and we can calculate Ka for that weak acid. Now that was acetic acid. So if we go to our data book, let's see if that agrees with what's in the data book. They don't always agree, but they're usually close. Whoops, I'm already at the bottom. I always have a hard time finding acetic acid on here, and I don't know why. There it is. So according to the data book for acetic acid, its Ka is 1.8 times 10 to the minus 5, and we had 1.7 times 10 to the minus 5. Yeah, so it's close. And I feel like I calculated this one, but I don't have it written down. And I feel like if memory served me correctly, it was 1.76. Which rounds to 1.8, but whatever, you can do the math yourself too. If you carry all the digits through, you may get a different answer. Maybe it is 1.8. Okay, so that's our first problem. We're going to do 4 today, so that's one of them. So now we're going to repeat the exact same pattern, but a new problem. Okay, so if you would like, if you think, hey, I got this, and you can pause the video and try this one on your own. If you're thinking you still need a little more guided review, you can just sit back, relax, fill this in your notes, and work with me on this one. Okay, so what have we got here? Sulfurous acid. So I'm just going to write this thing out. H2SO3 in water, aqueous liquid. It's a weak acid, so it's going to be less than 50% products. HSO3 minus, and there's our hydronium from the acid. Okay, so now I can do the equilibrium expression. Ka is products over reactants, concentration of HSO3 minus, concentration of hydronium over concentration of reactant, product over reactant. And we only need that because water is a liquid, so we ignore its concentration. Okay, so I can get the Ka value if I can get these 3 concentrations, and I can using our ice table. So they tell us that it started off with 0.4 mole per liter solution. So we set up our ice table. Started off with 0.400 mole per liter. There's no concentration to that liquid. As it moves forward and makes some product, we're going to gain 1x, gain 1x, lose 1x. So add them up. I plus C, 0.400 minus x, x, x. Okay, and we know x because we have pH is 1.17. So concentration of hydronium from the pH, 10 to the negative 1.17. is 0.0676. Okay, so there's X. So now I can substitute those in up here. I can store it in my calculator under X, 0.0676 squared over 0.400 minus that value. And I get a Ka of 1.4 times 10 to the minus 2. And we were looking at sulfurous acid. So let's just go see how we did. Sulfurous acid is right here. Oh, it agrees. 1.4 times 10 to the minus 2. So we get the exact same value that's in our data book. That is worth a smile. Okay. Good. So that's half of what you had to learn today. So now we're going to do the second type of ice tables, and then we're done. Okay, the second type of calculation involves Ka and allows you to predict the acidity of any weak acid solution. So you're going to use your initial, so you're given the initial concentration of the acid, and you're given the Ka value. And then this time you determine the equilibrium concentration of H3O plus, and then usually pH. Because once you've figured out hydronium ion, then you're usually asked to figure out pH as well. So predict the concentration of hydronium ion and the pH. So there we go. So this time you're not given pH, so you have to do a little more work to get that hydronium ion concentration. We have 0.200 mole per liter, so there's our initial concentration. And they give us the Ka value. So they give us an initial concentration and Ka. And that's what I had just stated up here, using the initial acid concentration and Ka. So this is the second type of calculation that you will see. Okay. What's your strategy to solve this one? How are you going to do it? So what do we got? Methanoic acid. HCOOH reacting with water to make HCOO minus and hydronium. So I'm just going to fill in what we have. On an ice table, we have the initial 0.200. Water is a liquid. And we have the Ka value. And we know that Ka is HCOO minus products, H3O plus over reactants. Okay, so we have the equilibrium law expression. We have the initial. Oh boy, how do we solve this one? So we know Ka, 1.8 times 10 to the minus 4 equals this whole thing. Okay, what do we do? So let's just stare at it and think about it for a second, and hopefully some inspiration pops into your mind. How can we solve this? Okay, well, we could fill in our ice table. We know we're going to gain, starting with zeros, lose X, gain X, gain X. So at equilibrium, we have X, and we have 0.200 minus X. Okay, so we have our three equilibrium concentrations, but they all have X. So how do we solve for X? We have this expression, and we have the Ka value. So what can we do? Graph it. Solve for X. Okay, I'm going to go ahead to the next slide where this is all being neatly solved for you. Okay, so here's what I just wrote out. Ka is X times X over 0.20 minus X. Graph it and solve for X. Now I'm going to pause for a second here. First few times I taught this course, it never really dawned on me that every single weak acid question always looks like this when you get down to this step. Because all of the weak acids are 1 to 1 to 1 to 1, you always get Ka equals x squared over the initial concentration minus x. Doesn't matter what weak acid is, you always get that same pattern. So guess what? We're going to save a ton of time. You no longer need to do an ice table for weak acids. You can just jump straight to this because the ice table gives you the exact same setup every time for these questions where you're given the Ka and you have the initial. So I'll just highlight those. If you are given the Ka value and you have the initial, you can graph it and solve for x. Boom. And so that's what we're going to do. We're going to graph that and solve for x. So in your calculator, y1 is the Ka value, 1.8 times 10 to the minus 4. y2 is x squared over 0.200 minus x. Graph it. And the x-intercept is, did I do this one? 1.8 times 10, yes I did. X is 0.00591. Now this example from the textbook, they rounded it up to 6.0 times 10 to the minus 3. But we're going to use that graphed value. It's a little more accurate. Okay, so there's X. That's the concentration of hydronium from our ice table. So that's the other thing you have to know. If you take the shortcut, you have to remember that X equals concentration of hydronium. So that when you graph it and solve for X, you are solving for concentration of hydronium. Now we can calculate pH. pH is negative log of concentration of hydronium. And because we didn't round it, we get a pH of 2.23. Boom, done, amazing. So that's the second type of problem. And on these ones, because you skip that ice table, it saves you a whole bunch of time. So hopefully you remember that little step. Okay, so now we have one last one to do. And this is repeating the same pattern, so you get to practice it. If you're confident, you can do this one on your own. And we're not going to do the ice table. We're going to take the shortcut. Ka is x squared over initial minus x. And we know it's hydrocyanic acid, so Ka, we can look it up. They do this often in Chem 30 because you have that table of relative strengths. They don't give you the Ka values. They say go look them up yourself. So I'm looking at my table right now. I'll just pull it up for you. Hydrocyanic acid is right here. Oops, next page. There it is. So its Ka value is 6.2 times 10 to the minus 10. Look up in data book. That is a very small Ka value. That means that's a really weak acid. It produces almost no product. Okay, so we have Ka value, 6.2 times 10 to the minus 10. And we don't know X, we'll solve for it, but we have the initial concentration, 0.500 minus X. So graph it. X is 1.76 times 10 to the minus 5. You will probably have to zoom in like crazy to find that x-intercept because it's such a small value. Your calculator may say no sign change or error. It can't find the intersect because it's so small, so close to zero. So you have to zoom in to that origin to be able to find that x-intercept. I like Z-box and stretching out a really small little box right around the 0, 0 origin to find that intersect. It is there if you've done this correctly in your calculator as y1 and y2. It is there and you should be able to find it. Okay, so once you have found the x-intercept, you now have concentration of hydronium. You can now find pH. negative log of hydronium, and you get 4.75, which is a pretty high pH because it is a very weak acid. So that makes sense. And 2 decimal places, 2 sig digs, because of this 2 sig digs. Okay, that's it. That's weak acids and Ka values. So to practice, in your study guide, page 372, there are 7 questions. And the answers, numbers 1 to 7, the answers are on the study guide, just not the complete solution. So you solve them, see if you are getting the correct answers. And today is Tuesday. We will have a Google Meet on, haven't decided yet, Wednesday or Thursday, where you can ask me questions about these problems. They're a little challenging until you get the patterns down. So I can go over any of those ones that you didn't understand on page 372 in our Google Meet. And we have a quiz and assignment coming up here based on all of this. So you got to dial it in, make sure you get it figured out. I've given additional textbook questions if you need more practice, and answers are in the back of the text to check your work if this isn't enough, but I think it will be. Doing 7 of these should lock the pattern in for you. Okay, that's a wrap, ladies and gentlemen. I will see you tomorrow when we do weak bases and weak equilibrium.